What are they and why are they used in the majority of electrical circuits we have today? An inductor physically doesn't look like this. It looks a bit like this.
An inductor, as depicted here, is made up of a coil of wire which can vary in thickness of wire and number of turns. The inductance, denoted by a capital L measured in henries, of any given inductor can be calculated using this given relationship. A thicker wire translates to a longer inductor or lowercase l value, which means inductance will be smaller and vice versa for thinner wire. The greater the number of turns and area the coil has, the larger the inductance value will be.
But the question remains, what does an inductor actually do in the circuit?
An inductor in a DC circuit like this will store energy in the magnetic field that it generates as the DC current flows through it, in accordance with both Faraday and Lenz's laws. This graph shows the process, like that of a capacitor charging up, of the current in an inductor. It is evident that for each time constant, the current across the inductor is increasing until it reaches a steady state value. As there is a change in current to begin with, the inductor produces a magnetic field that in turn produces a back EMF to oppose this change, and therefore we see resistance before the current reaches a steady state value. If the DC supply is switched off, the opposite occurs, where the magnetic field produces a force to oppose the dropping current, and this is where we see an inductor's ability to supply the circuit for a time with current itself. This is an inductor's main quality. For instance, if a light bulb is connected in series with a DC supply and an inductor, and the DC supply is switched off, the light bulb would not go out straight away, and rather stay on due to the current supplied by the inductor before it then turns off. The voltage across an inductor, as demonstrated in this graph, will decrease after time 0 for each time constant because it is directly proportional to the rate of change of the inductor, which is multiplied by the inductance value to get the voltage. Since the current across the inductor will go to a constant current value after 6 time constants, as shown in the previous graph, the rate of change of the current will become 0, and thus the voltage across the inductor will also go to 0. Because the voltage across a resistor is determined by Ohm's law, we can then see that the voltage will increase until it also reaches a steady state value, where the current in the circuit is at its greatest.
If you're still struggling with what the inductor actually does in the circuit, let's consider this analogy. Think of the DC supply as a pump pushing water current through a circuit. The inductor can be thought of as a water wheel in this circuit. Now, when the water is first pushed through, the wheel is stationary and so has a lot of resistance, just like the opposition caused by a magnetic field in the inductor. Now, once the water is pushed through more and more, the wheel begins to turn faster and faster until it reaches a point where there's no resistance. This can be thought of as when the current reaches a steady state value. Inductors are super important to today's electrical systems, being able to store and release energy quickly. And that's all you need to know about inductors.